Yeah, I'm a PhD student at the Institute for Complex Systems, and today I want to present a new WAL programming language which enables programmable waveform analysis. So I want to start this talk with a little thought experiment, even though this is a bit unusual for computer science, but let's assume you developed a brand new design which is going to be included in the next Open MPW shuttle. So tape-out day is approaching, you are very excited. However, the last tests show that there are some short performance drops from time to time. And of course, you have to fix these, find and fix the cause. So what do? You open a good old waveform viewer and start debugging. So here you are in a waveform viewer, you open everything up, and what do you see? Well, this is way too much data, this is information overload. So you zoom in a little. This is better, but still too much information. Some signals we cannot even see the values. So we zoom in once again. But now we are too close. So now we completely lost the context of where we are. We can't even see what happened 10 clock cycles before. What I want to say here is that waveforms contain incredible amounts of information about the performance of your design, correctness, data control flow, and also optimization possibilities. But there are some very hard problems there. So the first problem is that waveform debugging is a 100% manual task. Whenever you do a new simulation, you have to start from the beginning. And of course, this is very tedious, and navigating inside the waveform is slow. And really, you can only see a very small slice of the simulation at each time, which limits you to basically debugging simple problems only. So maybe the major problem here is that we cannot automate this, right? So normally here would the animation say, or can it? So we think we can with WAL, our new waveform analysis language, which is a domain-specific language that really lets you express the problems that we face in hardware development. It features specialized language constructs for the hardware domain. For example, the signals you have in your design are first-class citizens in the language. You have access to time information, which we don't have in other general-purpose programming language. You have information about the hierarchy, and also about logical relations between signals, for example, the signals of a bus. And really, you have more power here. You have more power than, for example, a system Verilog assertions. You can do more than just expressing true or false expressions. Really, you have the power of general-purpose programming languages. You can define your functions. You have lists. You have hash maps. You have everything you know. And you can even call external libraries. And because we implemented all in Python, this gives you instant access to 1 billion Python packages. So if you ever wanted to feed your waveform data to some neural network easily, you're already set up. You just need to import TensorFlow. I want to introduce some very simple WAL code here with a basic example. And let's say we have a bus with a request acknowledge interface. I guess everybody has seen something like that here. And we want to calculate the average delay on this bus. So the average delay, how long one request has to wait before it is acknowledged. And to do this, we can see two interesting states. So the first state is obviously the waiting state. So the interface is in a waiting state whenever we have a request set to 1, but the acknowledge is still set to 0. And we can express this using this WAL expression here. And I guess at this level, everybody understands this. And the opposite of the waiting state is the standing state. So the bus is standing whenever we have a request, and we also have an acknowledge. And what we want to do here is we want to count both states. And in the end, we want to divide the number of waiting states by the number of standing states, which will give us the average latency. So because we want to do this on a complete waveform, and here we can see, here we have 40 ticks, but in reality, you maybe have 10,000. So it's obvious you cannot do this by hand, realistically. So we want to go over the complete waveform. So we wrap our expression in a whenever operation. And this says, whenever the clock is 1, do the operation in the body. And what is the operation in the body? It basically detects the waiting and sending states here in this when operation, which is an if operation without an else clause. And when it detects a state, it increments a variable. And after we are done processing the complete waveform, we will just divide our states and print the result. And hardware designs most of the time contain many structural similarities. For example, often we don't have one of these handshaking buses, but maybe 2 or even 10, we don't know. So this is of course ideal for writing generic code. It enables us to take the same code we have written before for one interface and now evaluate it on any interface, on any number of interfaces. And I want to show a real quick example how we can do this here. And for this, in WAL, we have the grouping feature. So what we first do is we detect all groups that contain a request and an acknowledged signal. And then we take the exact same expression as before, but we modify the signals quite a little bit. Namely, we append a hash in front of the signal name. And what this will do, this will evaluate the expression from before twice for each bus. But when the expression is evaluated, the hash will expand the signal name so that the correct signal is called. And with this little modification, we can extend our expression from before to the complete design. And really, if you add a new instance of this handshaking bus, it will work automatically. Of course, we want to show that WAL is really applicable to real-world problems. And for this, obviously, we solved our own problems first. So I have 2 examples here. In the first example, we developed a Python application with a GUI. And this is a general waveform analysis program. You can load any waveform that you have, and WAL will detect XI buses contained in the waveform, any number. It doesn't matter. It doesn't has any. You don't need to provide any information really. And for each interface it finds, it will render some neat graphs about the performance and some other metrics. And then we had another problem. We were working with the VexRisk-V processor, but we had a hard time understanding how exactly the processor was working internally. So we wrote a very little WAL script. I think this is 50 lines of code, and it renders a nice HTML website with a table that shows the pipeline stages, and you can see the instructions flowing through the processor, which is also color-coded. And we also added some warnings or errors which were detected during the execution of the program that we were running. So this all was possible with just a few lines of code. To wrap things up, waveform viewing is highly manual, and there's so much we can get from waveforms. And with WAL, we can do programmable waveform analysis to do, for example, data aggregation or data visualization, or really we can express any complex queries that we or you want. And WAL is, of course, available as open source on GitHub, and very soon it will also be available on the Python package index. And if you want to get more information about WAL, there's a research paper available on our institute website, and we will also do a presentation in January at the ASP.DEC conference. So if you have any more questions, please feel free to write me an email. I will be happy answering you, and I will also be happy getting to know the problems that may be good problems for WAL. Yeah, I think that wraps up my talk.